And welcome back to Brains Are Beautiful. In today's episode, we're going to be going over imaginary numbers, and there'll be probably a couple videos on this. So this is more the intro to imaginary numbers, what they are, how they compare to other numbers you've seen in the past, and maybe some really basic math to explain what they are. For more complex math and properties and rules, see the next video. All right, so let's get started. So before we can talk about imaginary numbers, we have to talk about numbers we've already dealt with. So how about natural numbers? And I remember when I took this class, I always needed a review of what all these numbers were, so I'm going to give that to you guys. Natural numbers, I'm going to abbreviate numbers with the pound sign here. Natural numbers are counting numbers. Okay, and so basically those answer the question, how many? So how many apples do you have? I have 5 apples. How many siblings? I have 7. Okay, so things like that. That's a natural number. So the next type of number is an integer. And basically these are both positive and negative numbers. So you see these a lot. -5, -500, positive 232. Okay, so that's what an integer is. The next part is a rational number. And these are ratios. So let me write that down. And feel free to take notes with me, or you could screenshot this when I'm done. And a ratio would be like, say, 3/4. So you ate 3/4 of the pie. Maybe it's the square root of 9/4, where both 9/4 give a whole number when you take the square root of. You could take 0.27, maybe. You could take 0.27 with one of these lines above it, which means it repeats on and on forever. Or you could even have like 0.95. Okay, so those are all rational numbers. And then our next type of number is a real number. And these are anything that you can imagine on the number line. I'm going to say anything on number line. So this pretty much includes everything you've probably ever seen, other than there's no imaginary numbers. And there's no infinity. Because basically infinity is not really a number. You could do more research into this if you're interested, but it's more of a concept and not a number. So there's no infinity, and today's topic is imaginary numbers, so you're about to see what those are. Okay, so moving into imaginary numbers. What is an imaginary number? Well, it's basically its own type of number line you could think of. So if I was to show you an imaginary number, maybe you've seen this in your classes. It's I, that is the imaginary number, and that is actually represented, or I should say it represents, the square root of -1. So you've probably seen in your classes when you've dealt with square roots before that you can't take the square root of a negative number. Well, the reason that is because it's imaginary or complex. And so you're about to be able to take the square root of anything you ever want to take a square root of. So let me show you how this works in real life. So let's say you want to take the square root of -16. Well, before imaginary numbers, you'd say we can't. Well, yes, we can. We can actually say that the square root of -16 equals 16 times the -1. And we know how to break this apart. That's 16 times the square root of -1, which we know the square root of 16 is 4 times the square root of -1, which we just said that this is I. And so our answer is actually 4I. So let's do one more example so you guys can see and get the hang of this. Let's say we want the square root of -20. Well, we're going to start by saying the square root of 20 times -1, which we can break further into the square root of 4 times 5 times -1. Then we can break this into the square root of 4 times the square root of 5 times the square root of -1. And we can go further and say the square root of 4 we know is 2, and then we know the rest of this is square root of 5 because that does not become a whole number if you square root it. And then we can say that the square root of -1 is I. And that is our answer. Kind of looks a little funny, but that's how it goes. Okay, so now that we've said how to use the imaginary numbers, I mean, I know when I first started, I really want to know, so do these complex imaginary numbers actually exist? Yes, they do exist. And let me prove it. We're not going to take a lot of time to prove it, but you guys can research this further if you're really interested. But I know when I was learning this, I would have really liked to have seen this proof. So here we go. So there's 3 reasons they exist. The first reason is we can actually define a complex number to be a pair of real numbers. And since we know real numbers exist, then a pair of real numbers exists. Okay, second, we know that there are rules and properties of complex numbers that define a number line. And as we talked about in Algebra 1, and you've probably heard in your other classes, if there is a number line and there's rules and properties, it means they exist. Okay, and then the third little property here that tells us that they indeed exist is that there's actually an object that when squared equals 1. And it's basically the pair 0, 1. So if we kind of expand this out to prove it, we know 0, 1 squared, that'd be 0, 1 times 0, 1. And that is going to equal 0 times 0 is 0, minus 1 times 1, comma, and then we have 0 times 1 plus 1 times 0. And this whole thing equals -1, 0. And basically, we know this is the answer. The zeros along for the ride, and we know that if we look at the proof a, 0 and b, 0, and that equals ab, 0. So it behaves the same way as real numbers do. Don't get too hung up on this. It can be a little confusing, but it's not the main point. Don't let it confuse you or make you mad. It's kind of a proof. If you were to go further into math or want some explanation, there it is. So now that we have proved that yes, imaginary numbers do indeed exist, let's look at what happens when we start changing the power of imaginary numbers. So we already said that I equals the square root of -1. What about I squared? Well, we know that this would be the same as saying the square root of -1 squared. And we know from past algebra that the square and the square root canceled out, and we're left with -1, which that's what I squared equals. How about I cubed? What is I cubed? I cubed, we can do the same thing again, equals the square root of -1 quantity cubed, which we know is going to be negative times the square root of -1. This you could say is -1 times the square root of -1. And so we're left with -I. And then I to the 4th equals I squared times I squared, right? Because 2 plus 2 is 4, you add the exponents. And so we know that I squared is -1 times -1, and -1 times -1 is 1. So this is actually a pattern. If we were to continue this group here on, you're going to get the same thing over and over again. So let me do this in a different color. So if you were to do I to the 5th, you're going to get the square root of -1. If you were to do I to the 6th, you're going to get -1. I to the 7th, you're going to get -I. I to the 8th, you're going to get 1. And this is just going to keep continuing on, these 4 things. So basically what we're looking at is multiples of 4. And the multiple of 4 is actually a really nice trick for when you're trying to do big power reduction. And I'll show you what that is. And let's say we want to use an example, I to the 99th. Now, you know, it's going to be kind of funny. Your teacher's going to laugh at you if you try to multiply I out 99 times. It's going to definitely be a story for the faculty lounge there. I have to say, I did that when I was first learning it. So I to the 99. So what we can say is we can actually break that into a different power. So we could say I to the 96 plus 3. Okay, so that's exactly the same thing. And then we can break this down and say that 96, we need that to be a multiple of 4. Well, we know that's 4 times 24, and then plus 3. We can't forget that. And so since this is a power of 4 right here, we can actually just kind of ignore it. And so then we're left with I cubed, which we know that I cubed is -I. And that's the answer. So that's the shortcut version instead of multiplying I 99 times. So let's do another example. How about if we said I to the 18th? Which, I mean, if you multiplied it out 18 times, it wouldn't be too bad, but it still might be time consuming. So what's the nearest power of 4 that we know? Well, how about 16? So I to the 16 plus 2. Okay, well, we know that that would be I 4 times 4 plus 2, which this is a multiple of 4, so we can just kind of scratch it out. We get I squared, which we know I squared is -1. And let's do one more example. What if we had I to the 52004? So yeah, 52,004. Well, we can say I to the 52,000 plus 4. Which then what we're going to do is we're going to take the 52,000 and divide it by 4 because we need that multiple. So we're going to get I to the 4 times, I believe that is 13,000. The 13,000 times 4 is 52,000 plus 4. And so since this is a multiple of 4, we can just scratch it out. And we're left with I to the 4th, which we know is 1. And so that's going to conclude this video. For a recap really quick, we started with what the different types of numbers were, counting natural numbers, integers, rational numbers, real numbers. We went on to define I, imaginary numbers. We said that yes, imaginary numbers actually really do exist. We went on to do a few examples, and then we said what happens when I is raised to a specific power. And we did some examples with that. The most important takeaway is that I does exist, and these rules right here are so important. They will come back, and they are really, really useful. So feel free to screenshot this video, take notes, watch it again, and when you're comfortable to move on, go check out the next video, Imaginary Numbers Part 2, where we'll do some more math and properties with them and complex numbers. All right, thanks everybody for watching. Feel free to comment below if you have any questions, comments, or concerns. If this video helped you, like it, give it a thumbs up, and please subscribe to my channel. And remember, brains are beautiful.